Welcome to the SCCE Research Knowledge Sharing webinar. This is series 11. Okay, so I hope everybody is ready for this session. Okay, before we start, I would like to inform that this webinar is organized by School of Computer and Communication Engineering, Universiti Malaysia Perlis. And for this session, we will paste the link for the attendance in the chat room, in the chat box here. Okay. I hope during the presentation, everybody can turn off their microphone so we can clearly listen to the talk well. Okay. Okay. Before we start, today I would like to introduce to our honorable speaker, Prof. TS Dr. Kamal Zuhairi Zamli. Actually, thank you, Prof, for spending your time, your busy time, to share with us your knowledge. So on today's talk, the title will be on optimizing team formation problem using hyper and meta-heuristic algorithm. Prof. Kamal obtained his BSc from WPI USA in 1992 and MSc in Real Software Engineering from Center of Advanced Software Engineering UTM in 1992 and PhD in Software Engineering from University of Newcastle upon Tyne, UK in 2003. Currently, he is Deputy Vice-Chancellor of Research and Innovation in Universiti Malaysia Pahang. His current research focuses on search-based software engineering, software testing and optimization. Prof. Kamal also have a lot of research grant related to software testing from both government and industry. He also have a lot published a lot of very high impact journal. So without further delay, I would like to invite Prof. Kamal to give his talk on this optimizing information problem.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Can everybody hear me? Should be okay, yes?
Yes, Prof.
Okay. First of all, I would like to thank the UNIMAP, especially SCCE, for inviting me to give a sharing session. Thank you so much. Today, I'm going to introduce the idea of team formation problem. So let me share the presentation now. Okay. So bear with me for a while. Okay. So I'm going to talk about something called team formation problem using meta and hyper heuristic. Again, my name is Kamal. I came from UMP. So basically, what I'm going to talk today is I'm going to talk about the need for systematic information approach, and then modeling team exploitation problem, and some of solution representation, our Java implementation, and future work. So basically, I hope everybody know what is a team. Let's say, for example, okay, we have a dream match, okay, maybe Earth versus Mars, and you are selected as the manager, and you are to select the best team from the world to play against, football against Mars. And you're supposed to, find the goalkeeper, defender, winger, attacker, and so forth. So who would you select if you have this football team? So in the sense that maybe you have million of candidate footballers around the world, okay? typically when you want to select them, you look at their skill or competency, the salaries that they requested, because you have certain limited budget. Maybe you're looking for their age. Okay, so effectively you are forming a dream team footballer. So in other words, you want to build a team, and then you have to find, there are so many for you to choose from, and you have the criteria, and this criteria you choose to build them as into a team. Okay, so this is the idea of team formation. So we, in our work, sometimes people look into skills and competency. So in this work, we use skill and competency term interchangeably based on the context that we are using. And there are differences within the two, and some people say that skills are individual footballers, competency are how know each other, jigsaw, how each jigsaw fits into the whole picture. So basically, skills specific to a particular job, competency are a collection of skills. So in other words, but in our work, we say in context, we interchangeably use them within the context of the work. I will see this later. Now, teamwork is cooperative or combined effort of a group or person working together as a team or common cause. So as a team, we can achieve more. So you can see that even if you saw all the movies from, we said now that they're all movies are coming as a team. Now we rarely see, one movie with only a single person. So we see that everything is a team. So we'll see how we form a team. So we are making this team formation into an optimization problem. So now, so the idea is, why are we doing this? Why are we looking into the idea of forming a team? Now, if we look at the current business model that we had in the world now, okay, companies are trying to be lean. In other words, they're trying to be small. If you have a big, let's say you have a big company and you want, for example, Microsoft Windows. They want to build a Microsoft Windows, and what they do is, what Microsoft did is they hire people around the world, experts around the world. Okay, and when they hire expert, this expert can be not necessarily reside in a single department. It is often costly to do so. So they need a way to form a team. For example, okay, let's say if I want to build a company, okay, then what can I do is I can hire all the experts into my company and pay their salary every month. Okay, and I have a very, very big company. But what if the current business model now is you don't hire expert, you hire them as per need of the project. If you look at, for example, Shopee, maybe is the largest virtual mall, but they don't hire anybody. Okay, so and look at also Grab. Grab is the highest, maybe the biggest taxi company, but they don't hire any taxi driver. So the idea is that if you have a team, a company, you only hire a team when you need them. So you don't have to put them into monthly payroll. So in other words, if you have the expert in a unit for project A, you need expert in, for example, programming. So you only hire when you need. When you finish project A, you don't hire them. So you hire them as consultant, as experts. So the idea is that this is a new way of doing business where you can outsource the work that you do to other people. So you don't have to hire the whole world. As you need, you hire them. So these people may be distributed around the world, maybe cross-discipline. Okay. So the idea is that you want to hire and fire expert per project basis, and they are not paid under monthly company payroll. So how are we going to do this, support this way of doing business? How are we going to build a team that is per project basis and per expertise. So for example, if you look at the diagram here, you see many people here from different parts of the world. So the question is, how are you going to build a team from different parts of the world or based on their shared competency? So the idea is that, let's say I want to build a team with certain expertise, and these are the people in the team with the same expertise, and they're different team for different project. So you don't hire them, but you hire them as per need. When you need, you hire them as a team and you pay them. When they finish the project, you hire a different one. So as such, your company can remain small. So in other words, you don't have to hire all of them and then add a monthly payroll and then search for a project. So it works the other way around. So the new business model is that you become small, like Grab, for example. They don't have any taxi. Okay, so what they have, but they are the biggest taxi company in the world. So in other words, what you do is when there's a need, and we can recruit people as per need of the project. So this is the idea. So how to model? So in this case, how to model and form a successful team where teams are distributed across different continent, time zone with multiple organizations. So how to build a network of persons with shared competency skill to undertake the project that we have. So this is actually the team formation problem. So let me share with you. Okay, let's say, for example, I want to illustrate the problem of team formation. Let's say we want to model a software development team. Okay, now let's say the software development team, we have the expertise of the team. For example, you have one name, Kamal, for example, his expertise is software engineering, computational intelligence, and software testing. Maybe you have another guy, Zuhairi, same expertise. Maybe M. Nizam, at the timetabling, computational intelligence, software engineering expertise. Mustafizo as computation, engine, and optimization. Azad having this. So ideally, each individual that we are looking for as different expertise. Okay, let's say we have a project, okay, that requires the following competency. So in other words, for this project, I require some expert in software testing, some expert in engines, some expert in optimization. So how am I going to build a team from this requirement of the project, from the list of experts that I had? So how am I going to build a team? So this is the question. Now, if you look at this, you can model the team. Let me go forward, and then I'll go back to this. Okay. Now, assume that we are having a project requiring software testing, engine, and optimization. So what we can do, we can pick a team, for example, a guy with software testing. So all exhaustive possible team are, you can have Kamal because he has a skill of software testing. You can have Zuhairi because he also has a skill of software testing. And you have Mustafizo because he also has skill of engines. And then you have Nasir with a skill of optimization. So all exhaustive possible team are Kamal, Zuhairi, Mustafizo, and Nasir. In other words, I can pick this. I don't have to pick, for example, M. Nizam because he doesn't have the skill that I require. So I can have this skill, these people with this skill. Okay. Now, I can also look at one possibility where I can have 4 people in a team. I will describe this later, yes? But I can also have possibility 2, where I can have Zuhairi, which he has the skill of software, because we're looking for software testing, engine, and optimization. We're looking for these 3. So if you look at this, Zuhairi has software testing, Mustafizo has engine, and Nasir optimization. So if I take possibility 2, I can now build a team that can address the same project with the same requirement of expertise. I can also have a possibility 3, instead of having just Zuhairi, I replace also with Kamal because he also have the same skill. Okay, but if you look at this, okay, the possibility 4 is actually the most minimum number of team, hence minimum cost, with Mustafizo and Nasir only. If you look at Mustafizo and Nasir only 2 people, but we cover all the required skill. You can see that we require software testing, engine, and optimization. So if you look at possibility 4, now we have the most minimum number of people, most minimum, assuming they are the same cost, the least cost for forming a team to do engine, software testing, and optimization. Can you see this? We have only 2. So instead of having 4, having 3, so the best minimum team formation is actually from just Mustafizo and Nasir. So this is an optimization problem where we minimize the cost, assuming that they have the same cost. Even you can have different costs also, but in this case, we assume the same cost. This has the minimum number of people and the minimum number of costs. Now, going back to the model, okay? So for what we do is, from this database of expertise, we can form a graph linking cost for each of interaction between, for example, Aswari to Azad. What is the cost of interaction? And we find what is the cost of interaction from Aswari to Nasir, and so forth. Now, if you look at this, the arc represents the cost of interaction. For example, if you look at Al-Swari to Nasir, so we look at Al-Swari here to Nasir, they have a common skill called software testing. So the link cost between person A and B is defined as 1 minus skill A combined with skill B, the common skill A with skill B over the combination of skill A and B. This is, in Malay, this is called union, and the other one is called union. And this one, in Malay, they call it tindanan and penyatuan, okay? So what you have, skill A and skill B, what's common in this? And you see that Al-Sawari with Nasir, the common one is actually software testing, okay? And the combination of them is 1, 2, 3, 4, 5. Actually 4, because software testing is the same. So if you do this, you get 0.75 or 3/4, because 1 over 4 is actually 3 over 4, which is 0.75. So you can have the interaction between Nasir and this, is the cost is 0.75. And you'll see that also there is no Mustafizo and Kamal. There is no link between the two. Okay, you can see, oh, there is one, okay. One meaning that is very expensive, meaning there's no link, so the cost most, if there is, the lesser the cost, the better the interaction. I mean, there are many common. For example, if you have a common, many common, for example, then you have a zero cost. For example, Swari and Kamal, we are all the same, and there's no link with it because the interaction have zero cost. Okay, if no interaction at all, you have a maximum, which is 1 cost. So by doing this graph, okay, we can model, for example, if I look at the cost, let's say for all exhaustive possible team, meaning I select all of them except here Mustafizo, because the requirement does not require except Azad. The requirement does not require networking and artificial intelligence. You can see if I have the team of Kamal, Aswari, Mustafizo, and Nasir, the cost will be cost of Kamal to Aswari. We say this is Kamal to Aswari, which is 0. There's no link, which is 0. And you have cost to Kamal to Mustafizo, was Kamal to Mustafizo is actually 1. Okay, and then cost to Kamal to Nasir, which is 0.75, Aswari Mustafizo, Aswari Nasir, and cost Mustafizo to Nasir. If you look at each individual cost, you add it up, okay, you have the cost of 4.25. if you have this exhaustive team. Okay. Now, if you look at different possibility, if you look at Aswari Mustafizo, then we have Aswari Mustafizo, Aswari Nasir, Mustafizo Nasir, and the cost is actually 2.5. If you look at this one, the possibility 3, Kamal Mustafizo, Kamal Nasir, Mustafizo Nasir is 2.5. But if you look at Mustafizo and Nasir, the cost is 0.75. If you look at this, Mustafizo and Nasir, 0.75. And you can see that if you model this mathematically like this, we can have the cost of this having the largest cost, and this is having the minimum cost. So in other words, that is why with possibility 4 was the most minimum for cost. So here we have a minimization optimization problem. So in other words, we can minimize the number of team and minimize costs based on the requirement for selecting the team. Okay, so the idea is that we are looking into the best team with minimum cost. So in other words, your company can become lean, you can have a database of experts, and based on the requirement of the project, you can have an automated team searching process that you can build a team. So this is the problem that we are trying to solve. Now, a number of possibilities we can look into this. Okay. Now, you can, for example, some of the team you can also treat them differently with different costs. For example, as a skill of expert, okay, you can put higher costs. Maybe a junior, you can put lower costs. So in other words, this model, you can have total cost as interaction cost plus individual cost plus individual load balancing cost. So you can introduce different type of costs for you to be able to minimize the number of teams. You can consider interaction cost plus individual cost plus maybe load balancing cost. Maybe, for example, he has participated in many projects, so there are many costs for him because there's a load balancing for him issue. So there are many other costs that can be added to the model in such a way that so we can build a team, we can minimize the number of costs. Some of people also can extend it, view for this. You can also have a specific person. For example, whatever team is, I want this guy to be in my team. You can also model this. For example, I want Kamal to be in the team regardless of your selection. So in other words, so you can have other selection and you can add Kamal later as seeding to the project. You want Kamal to be part of the team, whatever, if not selected, you can do that also. So there are many, many ways to model the team. So if you want to model just with the interaction cost, yeah, you can do interaction cost, but you can model them in terms of, for example, salary scale, expertise scale, or even load balancing between, meaning, for example, if the guy is in many projects, maybe there's a load balancing cost for him that he has to do many projects, maybe, so the cost for him become higher, for example. So you can make this and you can search for this as optimization problem. So if you look at this again, based on this is logically, if you have 4 people, if you don't model other costs, you can see that you have higher interaction costs because many people. And here you have only 2 people and the cost is 0.75. So this is the most minimum cost. So if you are looking for people with certain expertise, for example, like this, we can automate that. If you have, say, 1,000 or 100,000 of people, you can automate, and the team can be found with the most minimum cost as optimization problem. So this is a minimum optimization problem. So having said that, okay, so what we do now, we look into team formation as optimization problem, and you look at this, the objective function is actually to minimize the cost. Okay, so the optimization problem is about finding the best solution from all feasible solutions, how to find individual expert and form a team. if you have limited number of people, let's say here you have not many people, here you have 2, 4, 6, 8, 10 times 2, 5 times, you have 50 people. So what you can do is you can, ask individual what your expertise, and then do an exhaustive search, and then build them as a team. You can do this, okay, if you don't have many people. Okay, remember that what we are solving for geographically distributed workers from different continents. Okay, and then we cannot be asking them individually because there are too many of them. So let's say we have millions of people, you cannot ask them individually what is your skill, so you cannot do this individually. So exhaustive search is possible. So you need to give an educated guess. Okay, basically you need a strategy given limited resource and time constraint, and you don't know the best solution for sure because there are too many in millions. So you can have good enough solution. In other words, you can form a team with good enough solution. Okay, so the idea is that you can build a team. So this team may be not maybe the most optimal, but you know that this is actually the best solution that you can get. Okay, so this is the idea of having good enough solution. So now, so the idea to do this, we want to solve this problem using meta-heuristic. So meta-heuristic, actually you have an objective function, and you have a way or search operator for you to modify the existing solution and get a new solution, and you have a way to assess the quality based on the objective function. So in our case, we are looking into a minimum problem where you want to get the most minimum cost that you can do to get the best solution. Okay. Now, maybe some people have seen this slide before. Basically, when you do meta-heuristic, there are two main components. One is called exploration, one is called exploitation. So different search space have different contours. Some have many peaks, some have only 2 or 3 peaks. So the idea is being able to explore and exploit effectively, regardless of the search contour, is actually the idea behind meta-heuristic. Okay. So in other words, you can do explore. Explore mean global search. Exploit mean local search, where explore, the displacement is large. Typically, any meta-heuristic, the update equation will be xt plus 1 equal to xt plus delta. When you explore, the delta are large. When you exploit, the delta is small. Okay, so when you do searching, you're bounded by search space. So this is the idea. And for example, when you explore, the movement for current move, the next move is actually the current move plus some big delta. When you exploit, xt plus 1 plus xt plus small delta, I mean you're actually exploiting. Doing local search is not doing global search. Okay, so this is the idea, and the idea is that search operators are made of random values. Okay, in other words, whenever you do the update, highly unlikely that the same place are visited twice if you do random values. So typically, these are random, related to some random. Okay. Now, so this is the idea. Explore. When you explore, you move very far. When you exploit, you move to your next neighbor. So this is the exploit you do to your neighbor. Okay. So sometimes people say that when you too much explore, you prevent convergence, because if the best one is here, you explore, you miss this, and when you exploit, you converge very slowly. Okay, too much exploit. Okay, for example here, same idea here. Okay, when you exploit and exploit. Okay. So search space in team formation problem. So the idea is that between team formation problem, the search space are actually the interaction between each of the individual node or individual person in the in the graph. So basically what we did is we built a graph. We built a graph, and this graph having an arc of the cost of interaction between each individual. Now, if the individual are having a common skill, they don't have any cost, meaning the costs are zero. But they are not having any common skill, their cost is 1, and they have some partial skill, and the cost are some fraction number from 1. The larger the number, meaning the less number of common skill. Okay, the lesser the value. For example, if I have 0.5, that means there are a lot of common between the two as compared to, for example, Nizam and Zuhairi, because the value is small, there are a lot of in common as compared to Zuhairi and Nasir, for example, is 0.75, meaning Nizam has a lot in common than Zuhairi than Nasir to Al-Zuhairi, because the cost is larger. You know, for example, Zuhairi and Kamal, they are having the same skill or competency, then the interaction is there, but with the value of 0. Okay, and for example, Kamal and Azad, if you look at Kamal and Azad, there's no common skill. For this reason, the cost is the most expensive one, is 1. Okay, and the cost is only 0.5 here, 0.5 here, and 0.75 there. So the idea is that when you want to solve this problem, first we have to build the competency graph for all the list of experts in our database. So we have to build this because this becomes our reference point for us to be able to compute the fitness function. Because, for example, if I have interaction between Zuhairi and Azad, the cost is 1. If I have interaction with Zuhairi and Mustafizo, the cost is also 1. Zuhairi with Kamal, the cost is 0. Zuhairi with Nizam, cost of 0.5, and they are interchangeable. Same, meaning Nizam to Zuhairi also 0.5, Zuhairi to Nizam is also 0.5. So the idea is that the larger the cost, meaning the less common skills, the smaller the better. So this is the idea. So the search space is actually the interaction between each node or between each of the experts that we're looking for. So this is the search space for a team formation problem. Now, what we do is we implement this team formation problem on Java, based on Java. So what we did is, first we look into something so-called the skill definition file, where a typical example, this is called skill definition file. You can give different names. So for example, we have a file or a database of a person identified using email. You can identify the person using email, using name, using IC number, passport number, whatever. And then you have to define the competency that he has. And maybe he defined himself, the competency that he has. And then you have to build this. This is what we call the skill definition file. Okay, so what happened is the user will define skill definition. And based on the skill definition, we can first do something called the cost extractor. Based on this skill definition, what we can do, we can calculate this cost. We call it through a tool called cost extractor. This interaction, we calculate each individual interaction cost. Okay, and then we also tabulated the skill extractor. So there's cost skill extractor. So the skill extractor is actually defining, for example, Kamal, for example, here, he's having a skill of software engineering, computational intelligence, and software testing. But he doesn't have a skill of timetabling, computation, engine, network. And so that's why for the bit that we have engines, this 3 bit, this is with 1, the rest is with 0, because he doesn't have any skill of the other one. Okay, and you can say the person mapping is first Kamal, and then the sequence is like this. So we have 6 person, skill 9. So what we did is the skill extractor will define this skill, will produce this database. Okay, and then each sequence is mapped into set of covering as lookup table. Okay, and then we also have a cost extractor, where we define, for example, here Kamal with Kamal, and the cost is 0 because you with yourself. And Kamal with Zuhairi, the cost is 0 because they are the same and common. If you look at Kamal and Nizam, the cost is 0.5. If you look at this, and then if you look at this, the graph that we had, Kamal and Nizam, the cost is 0.5. So we did this using a tool that we developed called cost extractor, where the cost extractor is essentially implementing the graph, lookup for graph. For example, Kamal and last with Nasir, 0.75. So with Kamal and Nasir, you can see 0.75 from the graph. Okay, this is Kamal and Nasir 0.75. So what we built this cost extractor as lookup table for our team forming optimizer. So we want to optimize the team because we define the skill, we extract the cost, communication cost, we extract the skill, and then we optimize the skill, and this optimizing algorithm will look into the cost and skill extractor from this lookup table, and then use a meta-heuristic algorithm to choose within different teams and to minimize the number of person or number of costs to build a team. So this is the idea that we have. Now, although we give you this format, for example, when we did this, we don't store them like this. We actually store them as matrices, you know. But to help understanding, we form this like this. But they actually in the form of matrices. You know, for example, the matrix of 6 by 9 matrix. So when we do lookup table, they are lookup as in terms of matrix. In terms of matrices, similarly, this is also a lookup table in terms of matrices. So in other words, then from there you can get the cost and so forth. So the other idea is that this is how we solve this problem, team formation. And what we do also is that for this one, what we do, we also model this as permutation. You know, for example, if you have 6 people here, the search space size is actually 720. So in other words, there are possibilities of, if I make this Kamal, Zuhairi, Nizam, so the different sequence I can have, you can have, you know, for example, Kamal, Zuhairi, Nizam, Mustafizo, Azad. I can have Zuhairi, Nizam, Kamal, Mustafizo, Azad, Nasir. So you have many different spaces. So when we have number large, we cannot generate exhaustive sequence. You know, if you have 6, we have 720 possible permutation of combination of team. Now, if you have, let's say, 10, it will be 10 factorial, 20 people, 20 factorial. So you cannot generate exhaustive sequence. You cannot search for each sequence exhaustively to find the best solution. So this is the idea. So to do this, we have to model a sequence, but you cannot make the sequence exhaustive because there will be too many possibilities to consider. Okay, so this is the idea. Now, this is the example of our skill extractor and cost extractor. So skill extractor will read the input skills, and then from that we develop new skills, and we built the matrix that we want to. And similarly, cost extractor, we did a cost. So essentially, the cost lookup, we did a matrix like this, and then skill, a matrix like this. For example, when you select certain thing, you know that, for example, M. Nizam does not have the skill number 3, so he doesn't have the skill of software testing. Azad, you know, he has only 2 skill, so the rest he doesn't have any skill. So when you model like this, now you're ready to do optimization. Okay, so here, as a lookup table, when you build a sequence, which sequence cost is uses the lookup table that we built from cost extractor and skill extractor. All right. So this and we implement this in Java. As you see, that's why you see our screen is black screen. Java, skill extractor, cost extractor. So we build this using Java. Okay. And this is the optimizer. For example, this is the problem that we did by hand just now. I've shown you by hand before. If you remember, we did this early when we showed this. The best one is Mustafizo and Nasir. So we did the same problem here, very small problem, just to illustrate the point. So when you do this, when we did this, and based on the lookup table and everything, we get this. For example, the best is Mustafizo and Nasir with the cost of 0.75. And you look at this, we use sequence to do this. See, the sequence are different. We instead of all permutate, we sequence them, and then from that sequence, we find whether the sequence have the skill, and in the end, we find the best sequence is actually Mustafizo and Nasir. So this is the best team with the most minimum cost. So we may generate random sequence and evaluate skill and cost cover some iteration T. Finally, we map the sequence back to the person identity. So what we did is we use the number 0 to represent Kamal so that we can easily, using mathematical sequencing, this 0, 1, and then later we map back 0 or 1 to Kamal and so forth. For example, Mustafizo and Nasir 3 and 5. So when we did the mapping, we said we get 3 and 5, and then we remap the 3 and 5 back into Mustafizo and Nasir. So this is how we optimize this. So now, we did this already. We did implement this an algorithm based on the butterfly algorithm. So but we found out that the butterfly algorithm having more complexity than other algorithm, but it doesn't matter. But we did implement this. The one result you showed just now is based on butterfly algorithm. So we did this, and actually we did more than this. We did as multi-objective. Instead of considering only one cost, we consider also load balancing. But the paper is still under review. So we submitted the paper to ISI Web of Science. It's under review. So, but this is what we did. But we did multi-objective though. But again, this is what we did. Now, how to implement this in any other Metaheuristic algorithm? So this is if there is a slide that's useful for people, this is the one. So what you did is first, let's say if we're looking 3 skills, okay. First, you generate a random sequence, update fitness of each sequence. Any random sequence, update fitness based on the cost, okay. And then for iteration 0 to maximum iteration, and 0 to maximum population, get the current I sequence, generate new sequence based on meta-heuristic search operator. For example, XT, this is the XT. You generate new sequence XT plus 1. Let's say the generated sequence is 243501. So go through each sequence. Let's say for sequence 2. So I'm looking for software testing, engine, and optimization. Okay. So I have sequence 2. Okay. Then I have number 2, which is MNISM. Okay. And MNISM have timetabling, computational intelligence, and software engineering. I don't have, MNISM does not have any of the skill I require, isn't it? Because he has only timetabling, which is not software testing. He has computational intelligence, which is not in this skill. So what happened is delete 2. So I delete NISM, but number of covered skills still does not change because NISM does not give me anything. Okay. Then I go sequence 4. When I go sequence 4, 4 is actually Azad, and Azad is having networking and artificial intelligence. So again, I delete 4 and no change in the covered skill because Azad does not have any of the skill I require. Okay. Now for sequence 3, now I have sequence 3. Sequence 3 is Mustafizo, and Mustafizo has computation, engine, and optimization. So he has engine, and optimization. So what happened is, so previously I delete 2 and 4 because it doesn't cover anything, but now I keep 3 because Mustafizo has the skill that I have. And then he covered engine and optimization. So now when I keep him, I've covered engine and optimization. So I delete this from the covered skill. That means I already covered 3, I already covered this. Then I go 5. Now 5, when I do 5, Nasir. Okay. For Nasir, I have testing and optimization, and testing is there. And optimization is also there. So I keep 5, so I delete the rest because I've covered. So when I covered this, I compute the cost of 3.5 because 3.5 is covering the skill that I'm looking for. Okay, so 3.5 so I keep 3.5. So if the fitness of 3.5, the cost of 3.5 is better than my best cost, so I update it, or better than the current sequence, I update the sequence. In the end, when I finish the loop, I get the best sequence for minimal cost from the population, and I print the best sequence. So this is actually the algorithm that you are in any meta-heuristic algorithm, you can implement this algorithm. And this search operator, for example, if you're using, I don't know if you're familiar, if you're using, for example, PSO, then you have this PSO is you have the velocity, and then the X is the velocity, and then this is the update operator for PSO, and you have other updates. For example, for GA, you have mutation, for example, then you mutate the original sequence into different sequence, and then you evaluate the sequence for whether or not it covers the skill that you require. Okay, and then you did this, and then you after its cost, you measure the cost, and then if the cost is better than the previous cost, you update, and then in the end you pick up the best. So this is actually, if there is a slide, you need to remember this is the slide if you want to implement the this team formation problem as sequence. Okay, so I've given you the model, so there's no doubt it's easily to implement once you're given this. Okay, this idea. Okay, so this is what we have done. Okay, and this is typical any meta-heuristic. Okay, implementation. So we have defined a data set in this our GitHub. So we have many data set. I think we have 5 now. Okay, so we have one data set which on coronavirus. Also, we define where the expertise we use a tool to extract the keywords from the papers for coronavirus. So we have the expert with different expert list from coronavirus, so that we can have an expert also. If you want somebody to find a certain expert in coronavirus, they can define the thing, and then our tool can find the best. So we are developing that data. We have the database, but we need to clean the data a little bit more. But we have ACM data set, where these are ACM papers with number of person with skills. Where number of person 3,702 with set of skill 5,000, 3,000 and 5,000 number set of skill. Where DBLP 5,000 person and 3,800 skills. This is not 1 MDB, yeah. This is IMDB, so it's not 1 MDB. So just in case people thought this is 1 MDB, no. So number of person this, and we have also our faculty. This is a dummy data set to test our algorithm. We have the dummy data set. This stuff from Faculty of Computing, PMP. So when we develop our tool, we use this small data set. Now we can use larger data set because we know our program is correct. So you can visit this and get the data set. Maybe you can play around, or develop your own algorithm to do team formation problem. So now we did experiments with data set, for example, 30 skills, 60 skills, 90 skills. We did this. These are the skills that we're looking for. Number 120, and this is an example of ACM data set. We have J. Balasri. This is his expertise. This person identified using email. You can identify because how we did this. We get this from papers. Okay, so we get email from papers and we get the keyword from the papers, and we have this. And then you can for ACM we have 3,700 skills, 5197 skills, and you can find for this ACM, for example. Yeah, we find 30 skill, 60 skill, 90 skill from this. Okay. Again, remember, we don't work with this directly. First, we use, as I told you before, we have a skill extractor, cost extractor. These are first converted to matrices before otherwise the thing will be very slow. If you rely on this, your reading of text will be slow. So what you did, we make into matrices, integer and float matrices. And we, for example, for this one, you have for skill is actually integer, but for cost we use a floating number, and then we build the database. Okay, and this is some sample output from skill extractor. This you get this, for example. J. Balasri has this skill: agent computing, distributed data mining, intrusion detection, but it doesn't have any of the other skill. It's impossible for you to look into individual like this, but this is as a result from this skill. Okay, and then we built this. Actually, in real life, these are just matrices, but we showed like this. That you don't have 32; there are more than this. You have to have a person here 32. Actually, the person is actually 3702. This is actually a partial output. Or 3681, the total number of person here you have. So they are paid partial, and ideally, if you keep everything as matrices, then you can as integers you can have large number of person. If you that are having the most minimum cost, a person of 27, because we have 30 skill. So logically, the most minimum, if you have 30 skill, the worst case you can have is 30 people. Yes, because 30 people, 30 skill, and the individual have all you have unique skill. So we have 27. So if you have the number of skill, let's say 40, then your algorithm is no good, because 40 means you have some redundant skill. So that's why we have 27 and 30 skill. And this is the most minimum set of team that we can build with the 30 skills that are required that we have set. So the idea here is that the question is, can I build a football team with this idea? So the idea is yes. If you have each individual, you can define each individual skills. You can build the team with the requirement that you want. Okay, and you can even have a seeding. For example, I want certain player in the team regardless. You can define them, and then the skill that you can delete from the current skill, and you can find the rest of other skill. If you look at politician, for example, if when you do Sheraton move, you know, when Dr. Mahathir is actually stepping down. So when Muhyiddin came in, he can also define a set of people from different parties at different skill. He may be able to use the algorithm to find the best, for example, minister that he wants for his government by having the minimum cost, having the skills, define the skills, and from that we can automatically find the best set of government for this. So there's many ideas. This idea is applicable in many areas. In other words, it can be defined in any, not only in project management, or you can also define this in football team, into other team where you need to build a team. So this is the idea how to build a team. Okay, so this is 30 people that 27 people that are required to pick up the skill that you want. Okay, now, so the idea is that can you do hybrids? In other words, yeah, what we did, we used butterfly algorithm, we implemented, and we are able to model and actually find the team that based on the skill that we require. So you can do hybrids also. In other words, so I'm coming here in the perspective of hyperheuristic. So the idea of hybrids is that maybe some of you have seen this slide because I've used this slide many times. A few years ago. So if you look at people, for example, if you imagine that this being a GA, this may be being a PSO, this may be a cuckoo search algorithm, this may be maybe a BET algorithm. So different algorithms have different way of updating the current solution to the next solution. Okay, maybe GA is a bit more on like local search bias. Okay, for example, mutation. If you mutate only one value, this is like local search. Okay, so different algorithms have different way of searching a particular kind of fish, for example. So the same kind of techniques, typically you get the same kind of results. So, but if I can combine different way, I can get better results. You know, for example, if I go to the lake, I use only one type of fishing equipment, I may get only one kind of fish. But if I use a different equipment, I may get a different type of fish. So the idea is hybrid is that one limitation of an algorithm can be compensated with the strength of the other algorithm. So this is the idea of hybrids. So if you argue with people, why you do hybrid? Hybrid because the limitation of algorithm can be compensated by the strength of other algorithms. Okay. So the idea of hybrid, typically you can have low-level hybrid, high-level hybrid. So one form of hybrid called hyperheuristic. So this is actually hyperheuristic, actually a form of hybrid algorithm. So my perspective is that kind of thing. Now, so low-level hybrid, for example, you can have a local search operator, maybe a global search operator for one particular algorithm, and you can marry this operator with a different operator. For example, this example, typical example. For example, you have a cuckoo search algorithm having this equation. So you insert the equation from TLBO into cuckoo. Okay, then you have low-level hybrid, meaning the cuckoo implementation having this only update equation, you take another update equation, you put inside here. Okay, for example, you put TLBO, so build a new one using this equation. So this is called low-level hybrid. Why low-level hybrid? Because the structure of algorithm changes. Meaning, you modify the algorithm. So in that, the algorithm is originally only one equation, but now you introduce a new equation here. And this equation based on different algorithm. So this is called low-level hybrids. Low-level meaning because you middle with the original source code and you change the source code with different source code. So the update operator changes. So this is the easiest form of hybrids. Okay, you can take, for example, put GA and put sine cosine algorithm into GA. So this is low-level hybrid, meaning you just change the equation. So the update equation now is based on also include GA. So this is the hardest part of hybrid to justify. When people ask you, why you hybrid with GA? Why not with BET? Why not with BSO? So this is a difficult question. When you did this hybrid, you better have a good justification, because this is the easiest thing to do. I can easily make one hybrid by today. So PhD students normally typically like to do this. You make one hybrid, you take another, you put into this, I make hybrid. Okay. So this is the easiest form of hybrid. This is called low-level hybrids. Okay, you can have a high-level hybrids. High-level hybrid can be in the form of, for example, if you have population-based algorithm, let's say you have PSO, for example, okay, you update the population PSO, and then you finish the search, and then you use BET algorithm to use the same population and make the update. So this is no internal change, but one after the other. Okay, you did PSO, all the population, and then you, based on PSO, you go into BET algorithm. Then one after the other. This is called high-level hybrid. Okay, there's no internal change. Remember that low-level hybrid where you change source code, you change this, maybe the structure. So this is called low-level. This is high-level hybrid. Okay, another high-level hybrid form is that you can have one meta-heuristic as a black box and running together in parallel, maybe, and you choose the best from each output because there's no internal change. Okay, this is also can be called high-level hybrids. Okay, remember high-level hybrid, there's no change in the source code. Okay, low-level hybrid, you change the source code. Okay, so another possibility, this is called high-level hybrid, where you have one algorithm, sine cosine. After completion, you run another algorithm, sequential execution to improve the population. So this is called high-level hybrid. Okay. Now, there's also another perspective called hyperheuristic. Hyperheuristic is actually meta of metaheuristic. Remember, you have, if you remember that there are different layers of optimization. Let me go to this. Then I'll go back to this. Yeah. So normally for optimization problem, the baseline is you have exhaustive search, meaning that you don't have any. What you do, for example, you have many people. You want to find the people from Unimap. What you do, you can ask them. Let's say you have 100 people. You want to find who are from Unimap. What you do is you can go each individual. One person, are you from Unimap? The guy say no. Next one, are you from Unimap? So here you can have exact solution when you do exhaustive search. However, if you have 1 million of people, you cannot be asking individuals. Are you from Unimap? Are you from Unimap? So you cannot be doing that. So this is the baseline, exhaustive search. Okay. Now the next baseline is heuristic search. Heuristic search, maybe you use something called educated guess. So, for example, you want the person from Unimap. What you can do is, first, educated guess is that maybe the guy from Unimap is wearing Unimap shirt, Unimap shirt. You have there's a Unimap so-called, every university, we have the so-called our official shirt that we wear. For example, kalau Unimap tu kalau biru kan, UMP kalau hijau. So you can do heuristic, so educated guess. Everybody yang berbaju hijau, berbaju biru, we say you are from Unimap. So this is actually educated guess. Maybe that guy is actually from UMP, but he borrowed a shirt from Unimap. So actually, his heuristic search may not be accurate also. Okay, so but sometimes if you do heuristic search, you cannot getting sure, because maybe in that day nobody wears the Unimap shirt. So you cannot find this. So educated guess is also sometimes problem specific. It's difficult to use. So that's why people come with meta-heuristic. So meta-heuristic, educated guess, but you learn from previous moves. Okay, and you also control exploration. It's much better than heuristic search. So meta-heuristics are more general than heuristic search rather than educated guess. Okay, and then now people come with hyper-heuristic, which actually meta of meta-heuristic. So it's actually exactly is that hyper-heuristic manipulate meta-heuristic to do the search. Okay, it manipulates meta-heuristic. So in other words, you have a different layer. If you think of it like a controller of meta-heuristic is actually hyper-heuristic. So this is the idea. So hyper-heuristic, you can control the whole meta-heuristic itself. So meta-heuristic is control the search operator. Heuristic search are controlling based on guessing. Exhaustive search are search of possibilities. So these are different baseline of optimization problem. How to solve optimization problem. So we are looking into something called hyper-heuristic. So basically, you can imagine this being as a controller of meta-heuristic. So you have a master controller and controlling your slave. Slave are meta-heuristic. For example, you can imagine, let's say, Hawk is being, let's say, PSO. Let's say Captain America is actually cuckoo search. Maybe this one is maybe sine cosine algorithm. So the idea is that the master will say, go slave, go and do the search. And when this slave go and do a search, if the search is improving, for example, previously you get a minimum value of 2. When he did the search, you get a minimum of 1. Then this sine cosine, assume this sine cosine has improved the search. So he will be rewarded because he has already get a good result. In the next iteration, this guy will be selected again to do the search because he is improved. Maybe in next search, he does not improve. So the master say, okay, now I'll send somebody else. So this is the idea of hyper-heuristic, where you control the meta-heuristic. The best performing meta-heuristic get an opportunity to run again. The one who did perform poorly will be penalized. Sometimes some algorithm put them in taboo search or anything or something like that. So this is the idea of hyper-heuristic. So the idea is, what if we can choose adaptively? Sometimes we can choose adaptively which one we want for us, and the adaptive decision is based on the current need of the search. For example, if you know that some algorithm is good for exploration, if your algorithm is stuck in local optima, you can select the algorithm with more exploration to do the search for you. So this is the kind of thing. So the idea of hyper-heuristic is actually a meta of meta-heuristic. This is meta-heuristic, this is meta of meta-heuristic, or the best name is called hyper-heuristic. So there's actually a simple one. Hyper-heuristic is actually a meta of meta-heuristic. So this is the idea. Now, there are two types of hyper-heuristic. One called generative hyper-heuristic, where the hyper-heuristic learn to choose a particular set of search algorithm based on certain problem, and something called also selective hyper-heuristic. And we did a lot of selective hyper-heuristic, where you can select between different meta-heuristic to do the search. Okay. Now, this is typical that we did. We have a Monte Carlo, we have cuckoo search, flower local, flower global. We can use the Monte Carlo to choose either one of these, and then based on that, penalize and reward. If this one, for example, get chosen and it produces a good result for next iteration, this guy will be select again because of its good performance. Otherwise, somebody else will be selected. So this is the idea of. So this is the part where the master is, okay, where we controlling the meta-heuristic and so forth. Okay, this is an example of our work we did. Monte Carlo hyper-heuristic, where now, if you look at this, the this is the meta-heuristic that we're controlling. When you do this, anybody familiar with simulated annealing? It's very similar to annealing. If they improve, if the previous objective function is improved, then keep the meta-heuristic that you're running now. Okay. If not, compute the probability. With some probability you keep, or that one you random select a different set of meta-heuristic to run in the next iteration. So this is a selection of meta-heuristic that you want to run. Okay, and then you select new search operator H1. That means you run H1 here. Okay, and this is keep the previous that you run. So this is the idea of hyper-heuristic, where you control the meta-heuristic operation itself. Okay, so that's what it's called, meta-heuristic. So example of generative, what we had is selective just now. If you remember, there are two types of hyper-heuristic. One is called selective hyper-heuristic, and the other one called generative hyper-heuristic. Now, for generative hyper-heuristic, what you do is initially you take a problem, okay, and then you learn from that problem for this particular problem. So the best you have, for example, let's say you have 20 meta-heuristic. Okay, so you take a problem that you fit in this, and it will select from the pool of 20. From that, you can do multi-criteria CBR, for example, case-based reasoning. Maybe out of 20, PSO, GA, maybe bad algorithm is actually having the best for this problem. For a different problem, maybe a different set of knowledge. For this problem, algorithm A, B, C, D. For the other problem, maybe algorithm E, G, H, I. So based on this problem, then this generative will select a different set of meta-heuristic for that particular problem. And then you can have this problem. That's as well called generative hyper-heuristic. I mean, more general, it can automatically detect what kind of problem, what kind of meta-heuristic suitable for that kind of problem. So this is the idea of generative hyper-heuristic. Now, we talk about this. How do we implement team formation problem using hyper-heuristic or meta level? Okay, and I remember now I have Venom in my diagram now. So because that would, when I was working in this slide last time, Venom has come out with a new movie, so that's why that includes that into even Star Wars also get included into Avengers kind of baby. So hyper-heuristic implementation, is it difficult? So the question is that how do you implement this? So the idea is simple. The changes you make is using selection hyper-heuristic search operator. So here you implement maybe the Monte Carlo one, which selects the hyper-heuristic here. But you have to implement a different set of selector to do the selection of hyper-heuristic to perform to generate the new sequence. So this is a simple change here. The rest does not change. You can implement the same team formation problem, but for using hyper-heuristic. So only this, if you remember the previous one, I don't have this hyper-heuristic. If you remember the old one, when we solved this problem before we introduce this, we say that here we have the meta-heuristic. The rest does not change, okay? But the hyper-heuristic, because you control the meta-heuristic that you want to select to find a new the update of the current sequence. Okay, so this is the hyper-heuristic implementation. Okay, so having said that, so I'm done with my my talk. So what we have talked today is we have talked about team formation problem, how to model team, and then how to make the team formation problem as optimization problem, and how to define the cost so that you can have a model of cost, and then you can use meta-heuristic algorithm to find the most minimum team cost that you require. And the cost can be in form of interaction. Maybe you want a cost of expertise. You might to use a new model to include, for example, salary of the guy as one of the objective function, or you can include, for example, you want a team leader automatically be selected. You select first before this program run. So there are many opens up new possibility for you to be able to construct the formation of team. This team can be done for example, forming consultant company, Viva Vose team, maybe selection of panel for Viva. So there's a lot of things we can do. A forming cabinet minister, and everything can be done. So I hope with that I've given you something. You can learn something from what I've said. So with that, I open up for question and answer. Thank you so much.
Thank you, Prof. I think this is very interesting. There will be a lot of questions for this. But before that, can we have a photo session before we start the Q&A? So I hope that everybody turn on the camera. Okay. So the committee will take a screenshot. So, okay, ready?
Okay.
So that you still have turn on the camera. Okay, thank you, everyone. Okay, ready? 1, 2, 3. Okay.
Okay.
Okay, ready? Okay. Thank you, everyone, for joining us. Okay, we will have Q&A session. I'm sure there's a lot of questions for this. Okay. Before that, I would like to remind everybody that please fill in the attendance form and as well as the feedback form for this session. Okay, Prof. So can we go to Q&A? So I have a few questions that are given to me directly. Okay, or do we want to start from this from Zahra Adnan in the chat box? She asking question, which is better to use low-level hyperheuristic or high-level in the optimization problem? For example, in case we want to solve timetabling problem.
Okay. There's actually there's no such thing as high-level hyperheuristic, low-level hyperheuristic. You have hyperheuristic. Those are hybrids. Low-level hybrid, high-level hybrids. So hyperheuristic, they are hyperheuristic. So if you want to do timetabling problem, you require algorithm. There's a lot of local search algorithm. I think if you're timetabling, normally if you use, for example, sine cosine algorithm or BET algorithm, not suitably useful for timetabling. Timetabling, you require a lot of local search algorithm. For example, simulated annealing, hill climbing, even GA is okay. A lot of single solution, not population-based algorithm for timetabling problem. So you require a lot of reported good results are based on simulated annealing or based on single solution, a local search kind of behavior, not a global search behavior. So that's why. For hyperheuristic, if you want to implement hyperheuristic, you need to implement a lot of local search operator. Local search operator meaning mutation, single mutation, swap between two current and the next one, where there's a lot of local behavior to timetable. My experience says that. So I hope that answers the question. Okay.
Okay, there's another question here. Each metaheuristic algorithm has its own strength and weakness. Now we have hybrid and hyperheuristic, like Prof explained just now. So let's say we are a new PhD student. How do we start to choose the algorithm for our research? How do we start as a?
Depends. What if you are doing PhD student, first particularly you look into new algorithms. If I were you, I'd find a new latest algorithm. Okay, based on the latest algorithm, then you pick the algorithm up. If you want to do hyperheuristic, then you can contribute on hyperheuristic. So I think, yeah, choose a new algorithm. Some people did, but they use an old algorithm. It's difficult to justify in the thesis. So it's better to use a new algorithm, and then from there you start, and you can turn them into hyperheuristic or improve the metaheuristic. That's why that's what I suggest. Okay. You can ask verbally. Okay. I don't want to can ask you verbally. Yeah, go ahead. Okay.
Proceed.
Tak dengar, kena
turn on ni mic. Okay.
Right. Okay. Assalamualaikum, Prof Kamal. Thank you for this very informative presentation. Okay. My name, I'm from UNIMED, School of. My new faculty will be Faculty of Applied Science and Humanities. So, dalam management, in the management, normally heuristic we refer to rules of thumb. Okay, so where we say that heuristic, so it means that there's a rule of thumb. Just to share lah, because they ada confused sikit tadi pasal low level heuristic and high level heuristic. It's not heuristic proceed. Right. Okay, my two questions, Prof. The first one, how do you define the value for the relationship between Nasir and the other guy, for example? That is the first question. The second question, can you share with us the demo of the system? Thank you.
Okay. All right. When you compare the two, when you have a cost relationship between the two, is based on how common of the skill that you had against the other guy. It's satu tolak the skill of A. Dia punya saya lupa dalam bahasa Inggeris tu, dia tindanan dengan penyatuan, okay? A dengan B tindanan over penyatuan A and B. Dia punya bahasa Inggeris kalau tindanan apa?
Set ke, Prof?
Set. Tindanan bahasa Inggeris apa? Tindanan bahasa Inggeris penyatuan. Penyatuan is union. Tindanan?
Subset, bukan subset.
Subset lah. Dia lah, dia A, tindanan, dia formula, there is a formula this. If you remember, 1 minus A and B and A is combined with B. Okay, from there you get the relation. Okay, and this is to be done mathematically. To be done by computer. You define the data files, the computer will did this for you. Okay. Secondly, what was the question secondly? The second question was the demo.
Demo of the system, Prof.
I did not prepare the demo. Maybe later. In the end, when I will do later because I have to set the system there. Okay. Later I'll do that. Okay, demo. I can share the screen. Okay. Before we end, I will do demo for you. Okay. Anybody else with question? Okay.
There's a question from Ali MI here. What is the difference if we use MCM and MCA? I'm not sure what is MCA.
Yeah, I'm not sure what MCM and MCA myself.
Okay, but I have another question here, which is maybe Ali can clarify on what is MCM and MCA. The other question here is on hyperheuristic algorithm. How does the time generate the result increase because we due to using manual algorithm as compared to using only metaheuristic only?
That's a good question. Okay, that's a good question. The answer is when you do, so you have to understand, let's say you have a population-based algorithm. Okay, now the interleaving changes happens at the population level. So there's no change in the performance, because you don't run the whole algorithm. You may run, let's say, typical metaheuristic, you have from 1 to maximum iteration, for population 1 to population n. So for population 1, use PSO. For population 2, you use maybe a GA. So you can do like that. So the interleave between the two. the performance time is insignificant. You see no difference. See, because you don't do the whole algorithm as the whole population, but as individual population, you interleave between the search operator from each algorithm. So that's a good question, but you don't have that issue. Performance issue, no performance issue. Same with metaheuristic algorithm. Insignificant, I should say. Okay. So the one Monte Carlo and Monte Carlo algorithm. Okay. Basically, when you say in Monte Carlo, we refer to the idea of coming from simulated annealing, where maybe historically I was meant to understand that the guy who created this simulated annealing was playing, was actually gambling. That's why you call it Monte Carlo. So the Monte Carlo I meant here is Monte Carlo. You have the probability, meaning if you know simulated annealing, when you have a poor move, you use a probability E minus F1 F previous over KT. If the probability, if you throw a dice, the probability is less than that probability, then you maintain the current, even though the current search may well be poorer, or the rest, or you change. So this is the idea of Monte Carlo. Okay. All right. What is in software testing? Which the algorithm would suggest either single or hybrid one? Oh, this is a question from Bakar Salim. Okay, we use a lot of hybrid ones. New papers that we had, we use hyperheuristic a lot. We don't use any single one now. Yeah, sometimes we can get good results. New papers that we write now, all hybrids. So previously no, but now okay. Anything else?
There's another question. Between local and global search, which one should we focus more to obtain best optimized result?
Okay, it depends on the search space, really. That's why you need an algorithm that is able to dynamically determine. For example, if you want to give a medication to a person, you have to first take his blood pressure, check sugar. So in some particular time, he may need sugar. In some other time, he may not need sugar. So you have to be able, your algorithm should be able to look at the search space and then decide whether you should global or do local search. So this is the idea of balancing between exploration and exploitation. You cannot decide. Let the algorithm decide using during runtime. For example, if I run many times using one algorithm and I get the same result, that means I'm not good at exploration. So the next, I should go and explore more. So for example, if my result is improving, every iteration is improving. So that means I need to do more local search because I'm improving. That means I'm close to the real result. So I should do more local search. So your algorithm should be able to decide based on the pattern of the result that you get currently for you to be able to explore or to exploit. So this is the idea. Okay?
Okay.
Any more?
Any more question from the participant? No question, eh?
Okay.
Thank you, Prof, for your input, for your sharing on your expertise today. We are very honored to have you as a speaker today. And then I would like to thank you everybody as well for joining us. Don't forget to fill in the evaluation form. Before we go,
somebody asked me to do a demo. So someone just now asked me to do a demo. I'll do a demo. If you want to keep in, you can stay. If you want to leave, you can leave. But I will try to do a demo.
Okay, thank you, Prof. So, okay, Prof will show some demo. So let's hope that the person who asked this
I hope my demo will work now. Okay, because okay, I will share the screen later. 3 minutes. Let me go into my directory first. Yes.
Okay, Prof.
Okay. If you want to stay. Then I will present, so I can share the screen, isn't it? Okay. Wait. I'll do 3 minutes. All right. See. Um, what is my data? Okay. So many of them. Not sure which one. Wait. Editor. Okay. February 2020D. Okay. I'll share with you something for now. Wait. Okay, you see me?
Yes, Prof.
Okay, this is my multi-objective one. Okay, you can see this is the information problem. This is some history that I did on the code. Alhamdulillah, you can see even that. Alhamdulillah, whatever. So these are some of the execution that we can have for different. This is multi-objective one. So this is the code that we implement for the information problem. But this is multi-objective one. So I will run this one and some of the code. So I hope the SCM file is here. So I'll take some of this. 30 scale, not too many. SCM is longer, so let me get the one is shorter. Start this one. This is very slow. So you see me in the screen? No, don't see the screen now. Do you?
We see the screen, Prof.
The black screen.
The white screen.
All right. Okay, I'll share with you I'm running it now.
Okay.
So I stop this and I share different screen. And do. Okay, yeah. Okay. So you're putting in trouble, okay? Staff cost expertise. Staff expertise. I have. Okay. Paste. Okay, let me get this here. Copy one. Copy. Wait, I cannot paste. Why? I'm trying to paste from, otherwise I have to write many things. Copy. Cannot paste. Okay. Run this. Something else. First, see. Okay, I'll share again. Present now. Do. So this is the input that I will put in, where I have a set of skill to find 30, and this is the database, the matrix that we had, staff expertise and extracted skill, cost. And then when we do staff expertise, let me share with you the screen. This is for our faculty. We have the staff expertise of share. We define the staff expertise of staff skill to find staff. Yeah. For 30 just now. Yeah. This is 30. You can see that the screen here, the 30 staff, 30 expertise that we are looking for. You see the screen, the white screen, isn't it? Now.
Yes, yes.
This is the staff expertise that we're looking for. 30 expertise. Medium process control, software maintenance, software usability, cloud computing, biometric. And this is the one that we are running now. Okay. We are running now with Indo. This share. This is the one I'm running now. So I will run this, and you will see that this is running for the. If you see the sequence, in the course, you see? Can you see that? These are the sequence and update sequence distribute. This is multi-objective one because I improved the algorithm already. So now it's trying from the staff faculty with 30 skills. So this one is searching the best into the best. So now this is running. Can you see it running? Well, of course, it doesn't make sense running because the and actually
let's see.
I have this one. I run 6 algorithms together.
6 algorithms together.
One after the other.
This is the Monte Carlo
no
algorithm. No.
No. This is the result that we had. We calculate not only we have 6 algorithms. We have NST, LBO, MOCS. So this is the algorithm we run. Okay, a high volume. We run naked mole red. This is multi-objective butterfly algorithm, and we have multi-objective Jaya, multi-objective Kupu search. So, and what we do here, we have this. Perhaps it doesn't make sense to you, but I will show to you the result. If you won't wait, I share with you because this is multi-objective. I will share with you. Okay. Results. Because you didn't tell me yesterday you were going to ask me to do this, so that's why I ran my latest implementation. So my latest implementation is, you can see this is the result I get from that run. Where we did multi-objective, 2 objective, where I minimize the interaction cost against minimize workload distribution, and we have 5 algorithms. can see that the butterfly one is the red one. CS cuckoo search is this one. You can see that naked mole rat has more range more. Can you see that it has a better solution because it for multi-objective it gives you a lot more exploration, because far left, far right, we have naked mole rat algorithm. The other algorithm can only find the solution a smaller range. So that's why here in this case naked mole rat actually is better algorithm than the other algorithm. So what I showed you now is multi-objective one, although when I give my talk, I don't talk about multi-objective, I talk about single objective, but we have implemented multi-objective one. The reason being that is that I've upgraded my code to be multi-objective. So if you want me to do a single objective, I have to revert my old code. Okay, so this is a multi-objective one. So we did the for team formation problem. So this is the result you can see. And you can see, if you know multi-objective, from this diagram, you can see naked mole has better exploration because it can explore the solution with different, even at the very far end, as compared to some other algorithm. For example, the blue one, the red one only here, but the blue one can, so you have extended more than that. Okay, so I've shown you this, but for single one, I cannot show you now because I have to find where I put the other one. I'm working on this one now. That's why I can show you now this one. Okay, I hope that satisfies the thing, that to show that actually we did the work. We don't just talk, you know, we walk the talk. So we implement this. Okay, we have this implementation. So this is actually now the paper on this is under review. So in ISI paper. So maybe I can share with you quickly. If I may share with you, browse desktop. This is the just a few minutes. Yes, sorry to make you waiting. Window. Yeah, this is the paper that we're working on this. Yeah, this is actually what we. So when you give us to give a talk, we have actually a new thing to talk about, the multi-objective one. And you can see some of the diagram you had is there in the talk just now. And this is multi-objective one. So this is the work we are doing now, multi-objective one. So we have the result already. This is the previous paper, but we have all the results. So this is a multi-objective one, what we did. So partly is this something called naked mole rat. Okay.
Very interesting, Prof.
Information problem. So what I given you actually a single objective one, but I'm working on multi-objective one. So maybe next time we talk about how to do multi-objective to do team formation problem. So
which one have better result, Prof? Single objective or multi-objective?
Well, it depends. It depends. Depends on the problem actually.
Let's say we add more limitation. For example, just now you are focusing on skill, right? And let's say we add limitation like you said we have only one leader. That one is considered as another objective, or we just add to the cost function?
If you add leader, I think it's a single objective still.
It's single objective.
Yeah, but if you want to add, for example, maybe number of person, number of person against cost, and each person at different cost, then they can be multi-objective. They can be multi-objective. So you can make this multi-objective. For example, for PhD student, for example, naked mole algorithm is a new algorithm. It's published in 2020, I think. If you look at naked mole algorithm, it's published in 2020. That's why I asked you, if you want to do, you do algorithm that is new. This one. like about 2019. So we choose a new algorithm and we implement this into the typical for PhD student, pick a new algorithm and solve this information problem. You can contribute there also, having a different algorithm to solve this. You can, that's why I always ask people to use, a new algorithm instead of an old algorithm. So there's a lot more room to contribute. So that's my opinion like that. So sorry, I cannot show you the demo. Next time, if you ask me again, you can contact me through email. I'll demo for you. By tonight, I get my old code, then I will show you the single objective one. Because I'm working on the multi-objective one. So there's the single objective one, I already, move away because I'm moving this. So, but I can show, no problem. Okay?
No.
All right.
You,
I hope that satisfies everybody. So thank you so much for people who come. Okay.
Thank you, Prof. This is very, very interesting. I know everybody is excited, still excited. They still didn't leave the session because there's a lot of information, and even you don't show the single objective, the multi-objective one is a lot more interesting, I think.
Yeah, but that's why I don't want to talk about multi-objective because I don't want people to get confused because today is more introduction. Multi-objective, they involve a lot more computing and a lot more for understanding because this is like a gentle introduction to information. Then if you, that's why I talk about single objective, but you can ask me multi-objective, we know how to do it also. So, all right. So thank you so much.
Thank you, Prof.
Okay.
For spending us your valuable time, although you are very busy.
No, it's okay. It's okay.
Okay.
All right.
So, is there any more question? I think that's all for today. Thank you, Prof. I think there's one requesting email. I think you can download the slide, and then there's the email. The Prof email is on the first page of the slide.
Yeah.
Is that correct, Prof?
Yeah, true.
Okay,
no problem. You can search for me. You will find.
You can search. Yes, Prof is. You can search in the publication as well. There's a lot of Prof publications, so you can see the email there as well. So again, thank you everyone for joining us in this session. Thank you, Prof, for your time. And it is very interesting topic. I know everybody want to do. I think this is quite a hot research topic right now. So everybody want to join in as well. So if you want to say anything, Prof, before we go?
No, just thank you for listening to what I've said. Maybe if what I said isn't is useful, take it. If it's rubbish, throw it away. Okay. So that's all. Thank you so much.
Thank you, Prof. So thank you everyone.
Thank you.
See you again on our next webinar. I think which is next week. Okay.
Thank you.
Bye.
Bye.